All right, this is a video for Algebra 2 on an introduction to rational exponents, and we'll start with a few reminders around exponents and rules of exponents, and then we'll do a few different solved examples. So our goal here is to really think about what this might refer to. What's 32 to the 0.6 power? Or equivalently, 0.6 is the same as 6/10, right? What's 32 to the 6/10 power? What might that be? And I want to acknowledge that that feels really counterintuitive. We've talked about exponents back in Algebra 1 and in earlier math classes in terms of a way of counting how many times something is being multiplied by itself. And that makes sense. We're counting generally using integers, right? So for our example here, 5 to the third, that really means 5 times 5 times 5. So 5 times itself 3 times, which is 125. And I think that makes pretty good intuitive sense to a lot of us. But then we start thinking about negative exponents. What does it mean to have something being multiplied by itself a negative number of times? And then today we're going to be talking about fractional or rational exponents. So just want to acknowledge that it's counterintuitive, but we're going to, as we often do in math, try to push the envelope and see if we can apply some current understanding to some new understanding and try to break some new ground here. So let's get through some reminders on rules of exponents. So as I just mentioned, and generally an exponent you can think of as a way of counting the number of times something is multiplied by itself. Let's do this next problem right here. Quick reminder about what a negative exponent means. That really means that we can place whatever the power is on the opposite side of a fraction and turn that exponent to be a positive number. Okay, so 5 to the negative third is 1 over 5 cubed. For many of these rules, there are real, legitimate, understandable reasons why these rules exist that I simply don't have the time to go into right now. So I have some videos in my Algebra 1 set that will really explain the background behind why these rules are true. But anyway, 1 over 5 cubed is going to be 1 over 125. Okay, so there's a quick reminder there. Another reminder about when we're multiplying powers with the same base, and so the requirement here is that the bases are the same, so 5 is the same, the 5s are the same, and they could have the same or different exponents. But a reminder there is, in this case, we would add those exponents together, 2 plus 3, and we would end up getting 5 to the 5th, or I can't do that in my head, 3125. And you could check that. You could do 25, which is 5 squared, times 125, which is 5 cubed, and you would get the same answer. In a similar situation, but it has a critical difference, when we have, in this problem right here, when we have a power then raised to another power, the rule is that we multiply those powers. Okay, so that's going to turn into 5 to the 6th. And that's going to be 15,625. And again, you could check that as well. You could turn this 5 squared into 25 and then do 25 cubed, right? That cubed would come down and you would still get the 15,625. So it does check out, the math does check out. Last couple ones, remember that 5 to the 0 is equal to 1. Anything to the 0 is equal to 1 as long as we're not doing 0 to the 0. 0 to the 0, it, by the way, is undefined. It breaks some math rules. And then as our last quick reminder, 5 to the 6th divided by 5 squared. So similarly to the multiplication rule where we added those exponents if the bases were the same, here we are allowed to subtract exponents if the bases are the same. And so 6 minus 2 is 4. So this turns into 5 to the 4th, which is 625. And again, you could check that as well. You could figure out what 5 to the 6th is, divide it by 5 squared, or 25, and make sure you do get a 625. So those are some reminders of exponential rules that you should already have seen, but I wanted to make sure that you got reminded of them, because we're going to apply a couple of them into kind of forging new ground here with rational exponents. So first I want to talk about the connection here between rational exponents and square roots. And I want to try to give you a little bit of a background. I don't want to just tell you the rule, I want to try to convince you that it's true and explain why. So let's say we knew that we were working with the square root of 4. And let's say we wanted to try to figure out, could we write that as an exponent? The square root of 4, approximately 1.4. Could we call that 4 to the something? Okay, well, let's try to do a little bit of work on what that might mean. I hope you can see down here the square root of 4 squared. That should just be 4, right? So this is going to turn into 4 right here. And then over on the right-hand side, I hope you can see that we're going to use our power rule. Where we're raising a power to another power, we need to multiply those powers. And so this is going to turn into 4 to the question mark times 2, right? Okay, really what I'm trying to say is these powers get multiplied. That was one of the rules of exponents I gave you a little bit earlier. All right, so let's work with this a little bit, and actually let's bring this over here where we have a little bit of space. I hope you're all okay with the fact that 4 is the same as 4 to the 1. Okay, so then what does this turn into? We have 4 to the 1 is equal to 4 to the something times 2. And what that really means is that 1 has to be equal to something times 2. Okay, 1 is equal to our question mark times 2. We could divide both sides by 2, and we get our question mark, or our unknown original exponent, is 1/2. Okay, so we have a half that can go up in there. And so really what all that means is that the square root of 4 is the same as 4 to the 1/2. And that's a pretty big deal, and that's what we'll be working with today. Okay, so to be absolutely clear, this is not the same as saying 4 times a half. Okay, 4 times a half is coincidentally also 2. Okay, but this really means 4 raised to the 1/2 power. Okay, that's really what that means. It's not a multiplication, it's a power, it's an exponent. So here are our rules down here. The first one is what I just mentioned. So a to the 1 over x, whatever a and x might be, is the same as the xth root of a. So as an example, 10 to the 1/3 is the same as the cubed root of 10. All right? Or let's see, 32 to the 1/5 is the same as the 5th root of 32, which is going to actually equal a nice whole number 2 here. Okay, so just a reminder about what those roots mean and how we put the little index of the root in the crook of that radical symbol so that we know what kind of a root we're taking. But let's extend this rule a little bit further. Okay, so we have the first rule we just looked at. Let's look at this next one. What if the numerator of our fraction isn't a 1? Okay, before the numerator of the fraction was a 1, but now what if it's a y? What if it's some other number? Okay, so we can apply one of our rules of exponents yet again and say that a to the y over x, let's just split that into 1 over x times y. Right, when we have a power to another power, that means we multiply those exponents. So y over x is the same as 1 over x times y. And then we can see that a to the 1 over x is just the xth root of a, all raised to the y power. Okay. Alternatively, we can say, let me use a different color here to point out where I am. Y over x is y times 1 over x, but we can multiply in the other order and say that this is all equal to a to the y, all then raised to the 1 over x. So that means we're dealing with the xth root of the entirety of a to the y. So all of those are legit ways of thinking about what a to the x is, and let me highlight just to summarize, or excuse me, a to the y over x. So a to the y over x is either the xth root of a, all raised to the y power, or the xth root of a to the y power. Okay, let's do some examples here. I have a few different examples set up for you. And I'll try to explain them in a variety of different ways just to make sure it really sticks with you. So A, 8 to the 1/3. That also means what to the third power is 8. And I encourage you to really start committing some of these common powers and roots to memory, but 2 is the cubed root of 8. So this is the cubed root of 8, which is then equal to 2. So 2 times 2 times 2 is 8. 8 to the 2/3. Okay, well, we already found 8 to the 1/3, so we can write this as 8 to the 1/3 then squared, right? And so 8 to the 1/3 is 2, and 2 squared is going to be 4. So that would be an answer. I want to show you a different method, though, to solve the same problem. We could also think of this as the cubed root of 8 squared, which is the cubed root of 64. What times itself 3 times gives you 64? Well, it's also 4. It needs to be the same answer, right? Otherwise, our system would break down. I prefer, if possible, finding the root first and then squaring, simply because we're dealing with smaller numbers, and that's often easier to do it in your head. But either way is legitimate. Let's do 8 to the 5/3. Here, I would maybe consider 8 to the 5th, then to the 1/3. Yikes. I don't want to do that in my head. I could always use a calculator for it, but I can't do 8 to the 5th in my head. So let's go in a different order. Let's do 8 to the 1/3, then to the 5th. And we should know pretty solidly by now that 8 to the 1/3 is 2. So 2 to the 5th is 32. 2 times 2 times 2 times 2 times 2. 2 times itself 5 times. All right, now we're going to get into some things that look a little bit different, maybe a little bit scarier, but we can still do them. What if we have decimals as exponents? Well, let's just turn those decimals into fractions. So then we can apply our rules. 32 to the 0.4, that's 32 to the 4/10. And then you might think, is there a 10th root of 32? Well, it's not very easy to do in my head, but let's simplify down that fraction. That's 32 to the 2/5. All right, and now we can work with that just using our common powers. That's the 5th root of 32, then squared. So the 5th root of 32 is 2, as we've been saying a couple times so far, and then 2 squared is 4. Okay, so the message there is turn that decimal into a fraction, and then reduce the fraction if you can. 27 to the 1.3 repeating. Well, 27 to the 1.3 is the same as 27 to the 4/3, which is then 27 to the 1/3, then all raised to the 4th. We're just pulling apart that fraction. 27 to the 1/3 is 3. 3 is the cubed root of 27. And then we need to think about what 3 to the 4th is. That would be 3 times 3 times 3 times 3. That's 81. And just want to know that you can do these in your calculator. So I encourage you can literally go 27 to the 1.33333333, type in a whole bunch of 3s, and you should get 81, or very close to 81 if there's a little bit of rounding involved. Let's do 8 to the 0.3 here. Whoops. So that's 8 to the 3/10. And then you might be thinking, okay, is there a 10th root of 8? That's easy to do in our head. No, there's not. I don't want to go that route. What if could we do 8 cubed and then find the 10th root of that? Okay, that's the 10th root of 512, or excuse me, to the 1/10, right? 512 to the 1/10. Well, that's not a common, easy to find one either. So you know what I'm going to do? I'm just going to go straight to my calculator and type this in. 8 raised to the 0.3. And what do I get? I get approximately 1.866. We'll round to 3 decimal places there. And that would be our answer for that one. So we don't always get perfect whole numbers. Nice. So rational exponents don't make intuitive sense maybe, but we can work with them by following the rules that we developed today. And we got through it, and that's a good place to stop.